Okay, so let's review about the mole since we've been away so long. Um, the mole tells us about how much is in a sample. It's like using a recipe. Instead of saying 1 cup of this and 1 cup of that, chemist will say, I need a mole of this, I need 2 moles of that. So if we have oxygen, we need to remember what the atomic mass is when we're talking about moles and mass. Remember, the atomic mass is this average of all the isotopes, and so it's a decimal. Um, if we want to round it, what we're going to be talking about with mass is we're going to be rounding. We're going to use the mass number, and for our moles, and we're going to round the nearest whole number. So if it's 15.999, that would round up, right? You look at the one to the right, that would round up to 16. And if we want 4 significant digits, 1, 2, 3, 4, it would be 16.00. All right, so we're talking about a mole, and the abbreviation is MOL. It just makes counting atoms easier. It's like, we're measuring things, and so it's a unit, all right? And it tells us how many particles we have, as in atoms, molecules, or formula units. Formula units would be like if I have water and I have H2O, right? I have 2 moles of hydrogen and 1 mole of oxygen. It tells me again the mass, 1 mole would be like the mass number. And the volume is how much space is occupied in a liter. All right, so we talked about, remember those great videos? A mole is 6.02 times 10 to the 23rd, and then that would be particles if you're talking about particles or atoms. This number here is Avogadro's number. Another scientist, Perrin, actually came up with the number. He calculated it, but Avogadro came up with the idea. So when he calculated this number, he named it after Avogadro. So a mole is like a dozen. It means you have a certain amount of things. If you have a dozen, you have 12 things. They could be 12 donuts, 12 flowers, all right? 12 dogs, 12 eggs, all right? A mole is similar to that. If you have a mole, that means you have 6.02 times 10 to the 23 things, all right? In this case, it would be particles, which is similar to atoms, molecules, or formula units. Okay, that would be 1 mole. All right, and so that's just a number that we're going to remember there. So if I said how many avocados are in 1 mole, it would be 6.02 times 23 avocados. Okay, it could be cars, it could be eggs, okay, it could be anything. A mole of marshmallows would cover the whole earth 12 miles high. So when we're measuring in mass, we can have a molar mass, all right, and that would be the mass of 1 mole of a substance. All right, so the molar mass is equal to the mass of the atom's masses from the periodic table. in grams. So when we're talking about molar mass, we're talking about the grams. And we're using the periodic table. So, for example, let me go ahead and put up my periodic table here. Oops, I did not want to do that. The molar mass of, if I'm looking at nitrogen, all right, the atomic mass is 14. I'm going to go ahead and just round that. That would be 14. I would round down to 14. All right. Let me see if I can get that back. Okay, good. Oh, no, now I'm not in Cami anymore. Oh, okay. Okay, so here I am. So now we're talking about diatomic elements, and those would be those 7 elements in the periodic table that are so reactive. All right, if I'm looking at my periodic table, starting with number 7, right, these 6 plus hydrogen are so reactive that they are always in a pair. All right, di means 2. So if it's diatomic, that means you're always going to have 2. All right, for example, you would have H. If I talk about hydrogen, it would be H2. All right, and here if I'm talking about fluorine, I'm talking about F2. I have 2 moles, all right, diatomic, 2 atoms. So if I want to know the mass of fluorine, I have to remember that I'm not just going to have 1 atom, I'm going to have 2, all right? So if one fluorine is 18.99, which I'm going to round to 19, if 1 fluorine is 19, this little subscript here, this 2, means I have 2 times 19 grams, so I have 38 grams per mole. That would be 1 mole. All right, if I just have an F2, that's assume that there's 1 mole. All right, so that answer there would be B. All right, so now I'm trying to find the molar mass of methane. All right, so I've got carbon and hydrogen, right? Carbon is 12 grams if you look on the periodic table, and hydrogen is 1. All right, now the question is, well, how many of each of these do I have according to the formula? If there's nothing there, that means I have 1 carbon. This 4 means I have 4 carbons. I mean hydrogens, 4 hydrogens. All right, so 4 times 1 is 4. All right, 1 times 12 is 12. So I'm going to add these together, and this will be 16. That's going to be my molar mass. All right, I have 12 grams of carbon and 4 grams of hydrogen, so altogether I have 16 grams per mole of methane, CH4. All right, now I've got calcium nitrate here. So if I want to find the molar mass, I'm going to look at each element, and I've got to see how many atoms of each of those elements. So I have calcium, nitrogen, and oxygen. Well, calcium, I only have 1 calcium. This 2 here, this 2 is saying I have 2 nitrates. That's what that means. So I've got calcium is, I'm going to look up here, see what is my mass of calcium. All right, the atomic number is 20. That means I have 20 protons, but though I'm looking at the weight for the mass, all right, and that's going to be the atomic mass, right? That's the average. So I'm going to take the mass number, which is just 40. All right, so 40 each mole of calcium there is 40. And then now I've got how many nitrogens? I have 2, right? This kind of gets like distributed here. So I have 2 nitrogens. And each nitrogen, if you look on the periodic table, is 14 grams. All right, let's find nitrogen. Here's nitrogen. Right, there's the atomic mass. The mass number is 14. All right, and I have 2 of them. And then oxygens, I have 2 times 3 because it's 3 plus 3. So that would be 6 oxygens. And each oxygen, if I look on my periodic table, my oxygen is right here. And so my oxygen is 15.9. So I'm going to round that to 16 for my mass number. All right, so 16. So that gives me 40 times 1, right? I only have 1 calcium. So 1 calcium, I have 2 times 14 is 28. And 6 times 16 gives me 96. And what I'm going to do is add them all up to get my total mass here. All right, 14, that's 10 plus 6 is 16. So 164 grams per mole of calcium nitrate. That's the molar mass. All right. Now here I have a covalent molecule, right? These are both non-metal. So it would be dinitrogen pentoxide. So I've got nitrogen and I've got oxygen. So I have 2 nitrogens, so that's 2 14s. And I have 5 oxygens, so that's 5 times 16. All right, so that gives me 28. And 5 times 16 would be 80. I'm going to add them up. So I get 108 grams per mole of dinitrogen pentoxide. All right, that's my molar mass. All right, now I've got sulfuric acid here. So I've got 3 elements, hydrogen, sulfur, and oxygen. I have 2 hydrogens, 1 sulfur, and 4 oxygens. Now what's the mass of each of those? Well, hydrogen is 1. Sulfur, I'm going to look on my periodic table. Here's sulfur. All right, the mass here, the mass number would be 32 if I round that. So 32. And oxygen is 16. All right, so that's 2 plus 32 plus 64. Right, I'm going to multiply those together. 4 times 16 is 64. And then I'm going to add these 3 to get the total molar mass. There's 98 grams per mole of sulfuric acid. All right, now I've got magnesium hydroxide. All right, so this is ionic, right? Because I have a metal and non-metal. Um, but I've got magnesium, oxygen, and hydrogen. I've got one magnesium, boom. Now I've got my parentheses, right? So that means I have two hydroxides. So that means I have two oxygens, 1, 2, and I have two hydrogens, 1, 2. All right, and the mass of my magnesium is, on my periodic table, I'm going to round to 24. So 24 for magnesium. Oxygen, I remember, is 16. And hydrogen, I remember, is 1. All right, so I'll multiply these together. 1 times 24 is 24. 2 times 16 is 32. 2 times 1 is 2. And I'm going to add them together to get my molar mass, the total. 4, 6, 8. So that would be 58, and that's grams per mole. All right. Beryllium oxide. All right, so let's see. Beryllium is over here. That's a metal. Oxygen is a nonmetal. So this is ionic, right? Metal, nonmetal. And beryllium is 9 grams. All right. So beryllium is 9 grams and oxygen is 16. Right, and I have one of each. So I'll just add those together and I get 25, and that would be grams per mole. Okay, so that is a molar mass. All right, that's a review of that. Measuring in volume, well, it turns out that if you have a gas, all right, a gas is going to have the volume of the space it occupies. All right, so if it's in a small space, it'll have a small volume, right? Gas can be compressed. And if it's in a big space, it will spread out, all right? So the volume of gas depends on the size of the container. If you have a mole of any gas, though, at standard temperature and pressure, STP, it is always going to occupy this volume, 22.4 liters. All right. And what is standard temperature and pressure? Well, temperatures wise, it's 273 degrees Kelvin, which is 0 degrees Celsius. 1 atmosphere. All right. Oh, okay. I didn't need to write that. I'll erase that. All right. So if I'm using Kelvin and an atmosphere, right, 1 atmosphere, it would be that. If I have Celsius, then I've got kilopascals, and it'd be 101.3 kilopascals. And we'll talk about that more later. What we're going to focus on now is this number 22.4 liters, all right? Because we're talking about moles, and that's the liter of 1 mole of any gas at standard temperature and pressure. All right, so if I have oxygen, which is a gas, and I want to find the volume, all right, well, if I have 3.5 moles, right, I have 3.5 moles of my gas over 1. And I want to convert that to the volume, right? Well, I know if I have moles here, I want moles down here. I know that 1 mole of any gas at standard temperature and pressure is 22.4 liters. 2 plus 2 is 4. All right? And that makes sense. If 1 mole is 22.4, then to get how much 3.5 moles is you times it. You multiply. 3.15 times 22.4. All right, but notice dimensional analysis wise, the moles cross out and that gives me liters. And that's always helpful. Then you don't have to try to figure anything out. You just let the units tell you what to do. And so 3.5, that's going to be your 78.4 just by estimating, right? Because 3 times 22 is 66. All right. And you can always put that in desmos. No, I didn't want to do that. Let me get a new tab here for desmos. All right. So it was 3.5, right? Whatever you're given over 1 times, and then it was 1 mole is, oh, not 1 mole on top. Because this was moles, so down here would be moles, right? And that 1 mole is 22.4 liters. And so I get 78.4. Okay. So we have a few things to memorize. We've got 1 mole is this Avogadro's number right here, 6.02 times 10 to the 23rd. And that would be particles. It could also be atoms, molecules, or formula units, or ions. Okay. And that's can also, if you have a mole, you can have a molar mass, which would be grams, which you get from the periodic table. So this is Avogadro's number. This is going to be the periodic table of elements. And this you memorize, 2 plus 2 is equal to 4. This is for gases. All right. Actually, I use a small g. If you're looking at a gas, that's what you're going to think of for volume. So volume, mass, and then number of particles. So solving mole problems, you're going to use your dimensional analysis. All right, your DA. I've been reading Harry Potter, so I'm thinking the dark arts, or what was their club? I think it was dark arts. Oh, what? I'll have to look that. I have to remember what DA stands. I'll have to look at that more closely. Anyway, dimensional analysis. How many moles exist in 23 liters of any gas? All right, well, if you have 23 liters, you always start with what you're given, right? Over 1 times. Now, if I have liters on top, then liters goes on the bottom. And then moles is what I'm trying to find, right? It says how many moles. All right, so I've got 1 mole is 22.4 liters. All right, and if this is on top and this is on the bottom of a fraction, remember fractions mean divided by. So 23 divided by 22.4, because this is on the top, this is on the bottom. All right, or just use your desmos here. What were we given again? 23. So Writing 23 liters. All right, but now the liters was in the on the top, so the 22.4 is going to be in the bottom, and the moles are going to be on top. So this can flip over. This conversion factor. This is called a conversion factor, and it can flip over because it's equal. These are equal. 1 mole equals 22.4. So you can flip it over. Technically, it's just 1. The units tell you what goes where. So this is liters up top, so this is liters on the bottom. And notice I get a little more than 1 liter. Okay. So what would be my best answer here? 1.03. We only had 23 liters to start out with, so it wasn't exactly too precise. So there we go. 3 significant digits. And remember, if you have 3 significant digits, the first 2 you know for sure, the third one is rounded. So if I'm looking at this, these 2 I know for sure, this third one is the one that's rounded. Okay, what is the molar mass of manganese cyanide? So let's see. So molar mass, I'm going to look at my periodic table, and I've got manganese, carbon, and nitrogen, right? I have these 3 elements. I have 1 manganese. Now this is in parentheses, so this 2 gets like distributed. So I have 2 carbons and I have 2 nitrogens. All right. All right, because what this means, if I have 2 outside these parentheses, that means I have 2 cyanides. So 2 carbons and 2 nitrogens. All right, but now I want the mass, so I'm going to look at the periodic table. Oh, I forgot my N. M-N. All right, I'm going to look at the periodic table and find out the mass of manganese. Here it is. It's a transition element, so it's 54.9. I'm going to round that to 55. Carbon. Let's find carbon. Here's carbon. And it is 12. And nitrogen is 14. All right, so I've got 155, 2 times 12, and 2 times 14. So let me do that here. So I had 1 manganese, which was 55, plus 2 carbons, which were 12, plus 2 nitrogens, which were 14. And so 107 is the molar mass, and this would be the closest one. Some people, when they're doing it, they go out to the 2 decimal places. We're not going to be doing that, but be aware. Okay, so now, how many molecules in Avogadro's number? So that would have to be this one. Remember, it doesn't matter what, this could be eggs, this could be flowers, this could be cars, it could be anything. What's important is it says how many molecules. All right, so aluminum is often used for the structure of lightweight bicycle frames. How many grams of aluminum are in 3 moles of aluminum? So I've got 3 moles of aluminum. So you start with what you're given. And you use the units because that tells you how to solve it. If I've got moles on top, I know the moles go on the bottom. And I'm trying to find out how many grams. So the grams goes on top. All right. So 1 mole of aluminum is how many grams? Let's see. Grams is on the periodic table. Here's aluminum. I'm going to round to get my mass number, which is 27. So basically, since these are both on the top, 3 times 27 is what I'm going to multiply, right? And I get 91 grams. And it's just grams because the moles crossed out, so it's just grams. And the question was, how many grams? So that is my answer, 91 grams. Oh, did I multiply wrong? I did. It's 81 grams. All right. So notice how you set it up with what you're given. Then the moles are going to cross out. This you get from the periodic table. Just multiply on the top and boom. All right, how many moles of copper are equivalent to this many atoms? So I've got 3. You start with what you're given. So 3.44 times 10 to the 23rd. And this is atoms, so that means I'm going to have atoms down here. All right, and it says how many moles, all right? So I'm going to do 1 mole. And then this would be Avogadro's number, right? 6.02 times 10 to the 23rd. And my atoms would cross out. I didn't write it up here, but this is atoms, right? That crosses out with atoms, and what I'm left with, oops, I didn't want to do that. What I'm left with is moles. So now I've got this on top and this one on the bottom, so I'm going to be dividing. And if I'm not sure, I'll just put it in Desmos. All right, so I've got 3.44 divided by all right, so I've got 3.44 and then that's times, and it would be 10 to the 23rd. Okay. Times, I guess I'll use parentheses, times, and then that was 1 mole per 6.02 times 10 to the 23. All right, and so there is your answer there, 0.571. And the atoms crossed out, and it is moles. All right. And so that's about half. And that makes sense because 3 is like half of 6, right? So that looks good. All right, and so notice atoms divides out. Atoms and particles, same thing. And you've got 1 mole, and you use Avogadro's number. Okay, so now how many moles of chlorine gas? All right, so now we're looking at gas, and we want volume. All right, so I've got 4.78 liters. Over 1 times, and then so liters is going to be on the bottom, moles is on the top. So 1 mole of a gas, of any gas, is 22.4 liters. So then my liters crosses out, and that would tell me how many moles. So I know I'm doing it right. I've got this on the top, this on the bottom, so I'm going to divide. So I've got 4.78 on the top, 4.78, and on the bottom, I've got that 22.4 liters, right? This is liters, and they're diagonal, and that tells me how many moles. All right, so 0.213 moles. All right. Okay, so here with the liters crossed out. Did I see that wrong? 4.78, 22.4. Did I type that in right? 22.4. Okay, so we're 21,213. So we're right. Okay. All right, so what is the volume of 3.5 moles of argon gas? Again, we've got gas and volume, all right? So, and this is true at standard temperature and pressure, so I've got 3.5 moles over 1 times, and then I've got moles in the bottom and liters on top. So 1 mole of my argon gas is 22.4 liters, right? My moles cross out, and then these are both on top, so I'm going to times them, right? So I've got 3.5, and then this was on, that was moles, right? So I had 1 mole on the bottom, and then my liters was on top. So mole, and then liters on top. And so that gives me 78.4 liters. And they rounded down to 78, right? If it's 0.4, you can round down, which makes sense too. I've got, this is 2 significant digits, so I can have 2 significant digits. All right, right? Here's 2 significant digits, and this has 2 significant digits. All right, so what is the mass of 37 liters? All right, well, if I have 37 liters over 1. Now, the nice thing is I don't have to look at the periodic table. It's always going to be 22.4, no matter what the gas is, liters. And that's always going to be 1 mole of any gas. So I think these are a little bit easier. All right, and my liters cross out, and then I have my moles. This is on the top, this is on the bottom, so you end up dividing. So I have 37 liters, and so diagonally I'm going to have my 22.4 liters, which means on top I have my 1 mole. And I get 1.6. I guess 1.7, right? If I use 2 significant digits, it'd be 1.7 moles. All right, so now in example 5, what was example 5? Oh, it said, what is the mass of those? Okay, so what is the mass? I figured this is how many moles we have, right? So we actually now need to take this moles, 1.7 moles, times, actually, you know what I'm going to do? I'm going to erase, because what you would do is you just extend this further, right? It's like a dimensional analysis can go forever. Like when we were doing the, years to seconds, right? You can keep going and going and going. So now I don't want moles, I want grams. Just when I was saying it was easy. All right, so we went from our liters to moles, and now we can go from moles to grams. All right. And we're looking at methane. So CH4. So I've got carbon and hydrogen. So carbon is 12, right? And I only have one of them. And then hydrogen is 1, but I have 4 of them. So 1 times 4 is 4. So, and then I have 1 carbon. So I have 12 plus 4, that gives me 16. 16 grams per 1 mole of methane gas. All right, so now my moles went away, and now I've got grams. So I'll keep this the same, right? But I have to keep going till I get grams. So I'm going to times by 16. So I'll put parentheses, and I've got 16 grams per 1 mole. All right, so I end up with 26.4. 3. All right. All right. And they left this off here. So this would be 1 mole is 16 grams. Okay. And that's filling this out, the 12, that's finding the molar mass. All right, so how many grams of nitrogen are present in 2 moles of nitric acid? Well, there's 1 nitrogen right there, right? So if you have 2 moles, right? So if I have 2 moles, that would be, well, there's 1 mole, HNO3. And if I have 2 moles, I have another one. So that means I have 2 nitrogens, right? And so I have 2 nitrogens, and each nitrogen is 14 grams per mole, right? So I have 2 moles. The moles go away, and then so that would give me 28 grams of nitrogen. All right, so your molar mass is 14, right? You've got 2 moles because it was 2 moles of HNO3. So you have 2 nitrogens, and this was your molar mass right here. So you have 28 grams. All right, so percent yield, do you always end up with what you want? All right, well, does everything go as planned? No. All right, theoretical yield is the amount of substance you should end up with if everything went perfect. The actual yield is the amount of substance you actually end up with. And you saw that in the Edpuzzle videos. The percent yield is like when we found the percent composition and the percent error. All right, you take your actual yield and you divide it, you compare it to what you were expecting, to the theoretical yield. all right? And usually you're going to end up with less, right? You're going to end up in a chemical reaction, you're going to end up with less than you expect, unless it's perfect, which it never is. So if the theoretical yield of carbon dioxide is 55.3, but the actual yield was 79, what's the percent yield? All right, so we're always going to have the actual over the percent, or not percent, over the theoretical. What was I thinking? All right, to make it into a percent, I'm going to times that by 100. All right, so the actual yield was 75.9. Now this is just a pretend problem so that to catch you, make sure you're reading it carefully, because what people tend to do is put the smaller number over the bigger number, because that's usually what happens. But it says here that the actual yield is 75. And we're going to divide by the theoretical yield, which is 55. Okay, that will give you a decimal. And then you convert that to a percent by moving the decimal over 2 times, which is timesing by 100. All right, so we'll do that, 75.9. 75.9 divided by 55.3. All right, 137%. And that's all there is to it. All right, so if they give you the theoretical yield and the actual yield, it's just a formula, and you just substitute in. All right, the tricky part is oftentimes you have to figure out the theoretical yield using a equation. All right, so if it's, here it says if you have 300 grams of zinc, the theoretical yield would be 9.18, and that's really nice. So they already told you that that was the case. All right, so if I want to find the percent yield, I would just take my the amount produced, right, which was my actual yield, 7.6 grams, divided by the theoretical yield, so it's kind of like when we did percent error, it's the same thing. All right, so 7.6 divided by 9.18. All right, and so that is, oh, then I'm going to times it by 100 to make that into a percent. Notice it just moves the decimal over, didn't change any numbers. So 77.99%. I don't know if that's okay. All right, the interesting part is up here to figure out the theoretical yield. All right, it's like what we were doing in those previous problems, where you just take where you just, it's just converting, just doing mole conversions. So you take what you've got. You were given 300 grams, so you put that over 1, and then you just keep converting until you find how many grams of hydrogen you can get. All right, so I've got grams of zinc, so how much is 1 mole of zinc? All right, and you just look on your periodic table. Let's find zinc. Here's zinc. Notice that's my 65.38, right? So that's your molar mass, right? And so then the grams of zinc goes away, and now you have the moles of zinc. But the thing is, I want to know about hydrogen, right? It says if only 7.6 grams of hydrogen. So I've got to switch from zinc over to hydrogen. And the way I do that is from this equation here. I look at the molar ratio. So this says 1 mole of zinc plus 2 moles of hydrochloric acid yields 1 mole of zinc chloride and 1 mole of hydrogen. All right. So what this means is if I want to convert from moles of zinc to moles of hydrogen, so here's moles of zinc diagonal, right? And then now I want to go to moles of hydrogen. I can do that because according to this, 1 mole of zinc equals 1 mole of hydrogen. All right, now that doesn't seem important because that's just 1 over 1, it's 1, but it's very important because that makes the zinc go away, and now I'm talking about hydrogen. All right, and it's not always 1 to 1. So now I've got 1 mole of hydrogen, and I got to remember, oh, that's diatomic, right? It's diatomic, so it's always with another hydrogen. So instead of 1 mole is not 1 gram, it's 2 grams. And then you would just type this all into Desmos. All right. Or on your calculator, it'd be 300 divided by 65 times 2. Whatever's on the top, you multiply. And when you have a number on the bottom, you're going to divide. All right. And that is the end of percent yield.